So welcome. We will now have the examples on torsion. So we have torsion problem exercises. So last time I have introduced to you all the principles regarding torsion as well as the formulas. So today we're going to apply that into series of problems. Okay, so for our warm-up, we have here a problem. A torque is applied to a shaft in which the shearing stress must not exceed 69 megapascals. So calculate the maximum allowable shearing stress, letter E, if the shaft is solid, and letter B, if the shaft is hollow. So if the shaft is hollow, as we can see here, there are two diameters given, wherein this is the outer and the inner diameter, meaning there is a hollow core along the shaft. As a solution, we recall the formula for torsional stress, which is expressed into this equation. Tau is equal to T R all over G. What is T here? The torque in Newton meter or Newton mm. And R here is the radius of the shaft, and J here is the modulus or the polar moment of inertia. So let us clearly define here what are the given. So of course 69 megapascal is referring to the tau here, and the maximum allowable T, or this should be the torsion, okay, maximum allowable T or the torque. So that we will just substitute 69 here and then solve for the J, solve for the substitute the radius, and then eventually finally solve for the torsion. So let us first determine the polar moment of inertia of a solid and the hollow shaft on the given A and B. For letter A, J is equal to pi all over 32 d raised to 4. And then we just substitute. We have the outer diameter of 100 raised to, that is raised to 4. And then J here will be equal to 9.82 times 10 raised to 6 millimeter raised to 4. So this is for the solid shaft. So by this, we can now automatically substitute this on the formula and then simply solve for the torque. We have here 69, torque is unknown, our radius is 50, and our computed J is 9.82 times 10 raised to 6. So as a result, we have an allowable torque of 13,551,600 Newton mm. So notice that in our formula, we use consistently the combination of the Newton and millimeter mode. So all of the forces will be in Newton, all of the dimensions will be in millimeter, and the stress should be equal to megapascal, so that we will have a consistent unit. So as a result, this is 13,551,600 Newton millimeter for letter A. Next, for letter B, we'll just apply the formula for a hollow shaft, wherein we'll just deduct the inner diameter of the shaft. So we have 100 raised to 4 minus 50 raised to 4 times pi all over 32. We have 9.2 times 10 raised to 6 millimeters raised to 4. So similarly, we simply substitute this J into our formula. Okay, so we have here the substituted values, and as we can see, R here is still 50 because the radius here is always referred into the outer diameter no matter what. Okay, so whether it is a hollow or a solid shaft, we always refer to the outer diameter. And as a result, we have a substantial decrease on the allowable torque of 12,701,360 Newton millimeter. So of course, the capacity of a solid shaft is different to the hollow shaft. So the solid shaft is a solid without a hole in it, and if we have a hollow shaft, there will be a hollow core into the shaft. So therefore, it is reducing the strength in terms of twisting. So that's it for the first problem. Okay, moving on to our next problem. So we have here a shaft ABCD. As we can see in the figure, it is restrained at both ends. We have A and D. So meaning it is prevented from a certain displacement in terms of angular displacement. So it is subjected to 1,200 Newton meter and 1,060 Newton meter at points B and at point C. So the given distance are given, as well as the modulus of rigidity equivalent to 80,000 megapascals. So we are going to determine what will be the torque reaction at A, the maximum shearing stress, the rotation between A and C in degrees. So we have discussed on the step-by-step method how to deal with certain problem like this. So the first step is to determine or the conversion of these torques into its equivalent force torques, that is represented by a double arrow. Now this is done by segment approach, but first we are going to convert the whole shaft considering the torques here. Placing the segments, converting our torque. So this is a clockwise, both are clockwise, 1,200. So that is represented by an arrowhead, a double arrowhead going to the right if we have a clockwise rotation. So these two clockwise rotation shall be restrained on A and D, wherein there will be a resisting torques against 1,200 and 1,060. And then by this, we consider section AA, left portion for segment AB, a cut section considering the left portion again for segment BC, and a cut section considering the left portion for segment CD at section CC. So notice that all of the section will be referred to the left portion because in this case we are after with the torsion at A. We do not want that one of these section will consider the right portion because it involves TD instead of the torque at A. Now considering these sections, at AA we have here the configuration. Only torsion at A is included. So that the segment torque at AB, I'll just assume it to be towards right. So this is what I wanted to emphasize, that we always have a consistent assumption of the torque per segment that is always towards right. So do not assume a leftwards direction for any torque per segment. Why is that? Because for consistency purposes, we are going to have one direction assumption, and then we'll just have to rely on the result of the equation, so that the equation will tell us whether our assumption is wrong or correct assumption. So therefore, by summing up forces along the axis, we can say that TA is equal to TAB. So moving on at section BB, so this time 1,200 Newton meter is already included in your section. So now again, we are going to assume a direction for the torque at this segment that is going towards right. And this is actually for the segment BC. So summing up forces along this axis, we have a leftwards TA, and then a rightwards 1,200, and a rightwards TBC. All of these will be equal to 0. Solving for TBC, we have TA minus 1,200. So moving on to the third section, section CC. So section CC actually involves both torques at the center, including the reaction torque at the leftmost support. So again, we are going to assume a direction for the segment CD. So we have that. And then perform equilibrium equation along the axis. We have a leftwards TA, a rightwards 1200, another 1060 rightwards, and TCD is of course rightwards. All of this will be equal to 0. Solving for TCD, we have TCD is equal to TA minus 2260. So these are now the equations of the torque per segment. If you notice that all of the segment torque is in terms of a single unknown, that is TA. This is actually the effect of having a single portion to consider in your section, all in terms of the left side, which contains TA. So continuing, we now write the rotation equation. And what will be our criteria here? Let us assume, or let us bear in mind, that along A and D, these are restrained. So therefore, there will be no rotation at A to D. So that we can say that theta A to D, the rotation is 0. Expanding this AD or rotation at AD further, we have equal to theta AB plus theta segment BC plus theta segment CD. We now write 0 as its value, and that is TL over JG of AB plus TL over JG of BC and the TL over JG of CD. We just continue. T of AB, remember that this is equal to TA. And then the length of the segment AB is actually here. That is equivalent to 4,000. And by the way, we have a common value for JG because we have a constant cross-section along all over the length, as well as the same material or homogeneous material from A to D. So this denominator will just merge into 1. We continue to write the torque at BC. And the torque at BC is this one, TA minus 1200. And then the length of BC is this one. We have 2 meters. Plus the torque along CD. So we have here TA minus 2260. Okay. So for the length of CD, we have here the length of CD, that is 3000 millimeters. So that is the 3000 there. In the meantime, we do not need to write or expand this JG here because it will just multiply to 0 by cross multiplication. Okay. So what is left is this equation. So the answer here is 1020. And what will be the unit? So we refer to the problem. If this is the given here, we adopted the same. We have not converted this into mm or whatsoever. So therefore, this will be adopted. Now, the usage of 4,000 or the distances in terms of millimeter will just have to cancel because we have a 0 number here on the left side. So it does not matter. So what is important, what you have adopted in the given should be followed. That is Newton meter. So this is actually the first requirement in the problem, the reaction at A. So what about the maximum shearing stress? So of course, we need to investigate what are the values of the segment's shear stress. So for segment AB, we have TAB is equal to TA. And this is the value. So for segment TBC, that is TA minus 1,200. We have here negative 180. So what does it mean to have a negative here? This is a wrong assumption for the direction of TBC. So therefore, our TBC should be a counterclockwise rotation as a result of the negative sign. So we place the unit Newton meter. And then TCD is TA minus 2,260. So TCD similarly have a negative value. So it just indicates that we have a counterclockwise rotation. So if we look at the magnitude, the most or the largest torque here per segment is obviously TCD, which is 1,240 Newton meter. So this will be adapted on the maximum shearing stress that is required on letter B. So by that, for letter B, maximum tau is TR all over J of segment CD. So substituting the values, we have 1,240. We need to multiply that by 1,000 to make it in Newton mm. And as for the radius, we need to refer back to our problem. So the shaft ABCD has 60 millimeter in diameter. So therefore, the radius is 30 millimeters. Okay. We place it here. And then for the J, we have a solid shaft. Pi all over 32 times D raised to 4. So calculating the maximum tau, we have 29.24 megapascals. And then for the third unknown, we have here the rotation between A and C in degrees. So to do this, we are going to write the rotation equation from A to C. And that will be equal to theta AB plus theta BC. And remember, that is no longer equal to 0 because AC is a portion on the segment that is not covered by the restrained support. So the restrained support is actually on torque at A and on the edge of D. So theta AC is somewhere mid of the shaft. So there will be a value for this. We'll just compute it according to the formula. We have TL over JG of AB and TL over JG of BC. So speaking of rotation, we need to substitute what we have computed a while ago, the values here, considering also the sign, because the sign will indicate the direction, whether it is clockwise or counterclockwise. So we have, first for AB, we have the torque at AB was 1,020 times 1,000 to make it in Newton mm. Length of AB is equal to 4,000. So plus the torque at BC is negative 180 times 1,000 times the length equivalent to 2,000. All of these shall be divided to the J, which is pi over 32 times 60 raised to 4 multiplied by the modulus of elasticity, which is given the problem, that is equal to 80,000 megapascal. 80,000 megapascal. So as a result, we have the rotation from A to C is 0.0366. And what will be the unit? Remember that it is in radians. So we need to convert this into a degree unit. Wherein in 2 pi radian, there is a 360 degrees rotation. So multiplying this, we have finally the answer 2.094 degrees as a rotation from A to C. So that's it for this problem. I hope that this helps, and I think you need to practice more problems. Thank you. So we have another problem here on the torsion. So this is actually just a warm-up problem. So determine the required diameter of a solid shaft to resist a torque of 15 kN when allowable shearing stress is 75 megapascal. So allowable shearing stress, we'll just write that and involve this formula. Tau is equal to TR all over J. Hence, we have 75 equals 15. This is kilonewton meter, so we need to multiply 1000 to make it Newton. Here is the 1000. And another 1000 to make it in millimeter. Radius here shall be in terms of the diameter. All over pi all over 32 times d raised to 4. So as we can see, in the equation, we have a single unknown, that is d. So we can compute that right away. We have equivalent to 100.62 millimeters for this diameter. Okay, so that is a minute problem. So next problem. So we have here a bar of cross section is 2.5 meter long. For 2 meter of its length, its diameter is 200 millimeter, while for the remaining 0.5 meters, its diameter is 100 millimeter. So there is transition of the cross section. We have a 2 meter and a 0.5 with different diameter here. So the bar is firmly supported at its end and subjected to a torque of 50 kilonewton meter applied at the change of the cross section. So if shear modulus is 8,000 Newton per millimeter squared, we are required to determine the shearing stress at the 200 millimeter diameter and at the 100 millimeter diameter bar section, and the angle of twist at the point of application of the torque. So basically, we need to determine or illustrate the figure according to the problem or according to the conditions of the problem. First, we have here the cross section of 200 millimeter diameter for a 2 meter length and eventually reduced at length of half meter, and this is 100 millimeter diameter. So both ends are restrained. Here it is. And a torque is applied at the change of cross section. This is equivalent to 50 kilonewton meter. So again, we are going to have our step-by-step approach. We call out the free body diagram and then convert first our 50 kilonewton meter into a double arrow towards right because this is a counterclockwise or a clockwise moment. Of course, to be resisted by 2 torques at both support. We still do not know the numbering here, so we need to number the or letter or a code here per segment. So I'll just name ABC so that this is TA and that is TC. We'll now place cross section AA considering the left portion and another cut section BB considering also the left portion. We get the torques segment by segment according to our section. So at section AA, we have this one, say this is torque at A being covered by this section. Then we assume a rightward direction for the corresponding torque at AB. Here it is. Equilibrium equation at along its axis, we have TAB will be equal to TA. And then at section BB, we have 50 now is already included in the section. Of course, TA. Just the same, a double arrowhead towards right. And then equilibrium equation on the axis. We have a leftwards TA, rightwards 50, rightwards torque along segment BC. These are all equal to 0. Solving for TBC, we have TA minus 50. Then we write the rotation equation from A to C, wherein A and C are restrained so that a 0 rotation is incurred. We expand the theta AC. Expanding it further, we have TL over JG for AB plus TL over JG of BC. We just equate that to 0. Substituting it further, TAB is TA here. The polar moment of inertia for 200 mm diameter. And the 8000 modulus of rigidity. So we add the other torque at BC. TBC is actually TA minus 50 times a half meter length all over a polar moment of inertia for 100 mm diameter times the same modulus of rigidity, that is equal to 8000, and those are equal to 0. So solving now for TA, we will have an equivalent of 40 kilonewton meter. So kilonewton meter again came from the given 50 kilonewton meter. So just be consistent with all of these unit. So remember that TA is also TAB and TBC is TA minus 50. 40 minus 50 is of course negative 10 kilonewton meter. So we already have the two torques per segment of the shaft. So we now compute the corresponding shear stress per segment, wherein the shear stress at 200 diameter shaft is actually that of segment AB. Substituting the values, so we have AB, that is 40 kilonewton meter, will have to be multiplied by 1000 to make it Newton, and another 1000 to make it millimeter. Radius is the half of 200, that is 100, all over J, which is pi all over 32, 200 raised to 4. Therefore, the shear stress at the 200 mm diameter shaft is 25.46 megapascals. So for the 100 mm diameter, it is actually the shear stress along that of BC. We again substitute, that is 10 multiplied by 2 sets of 1000 to make it Newton and millimeter. And then the radius is 50. So we divide this by pi all over 32 times 100 raised to 4. So therefore, the shear stress at 100 mm diameter section is 50.93 megapascals. So by this, we have solved for the shear stress per segment of the shaft. And then for the last unknown, we have to read this again. The angle of twist at the point of application of the torque. And where is the point of application of the torque in our figure? It is actually theta B. We just write the rotation equation for theta B, wherein this is equal to theta AB. Further, it is TL over JG of AB. The torque at AB is 40 multiplied by 2 sets of 1000 times the 2000 length here, okay, divided by the polar moment of inertia involving the 200 mm diameter section, and of course the modulus of rigidity, which is 8000. So finally, we have theta B to be equal to 0.063. And what is the unit again? We have a radians unit. Converting this to degrees, we have 2 pi radians is equal to 360 degrees. Therefore, we have a theta B equivalent to 3.64 degrees. So this is actually the angle of twist at the point of application of the torque. So this is about this problem. So I hope you have more practice and have a good day.